Good morning, fellow Form 4 students. We are back again, and this time around we are doing it live. In our last class of additional mathematics, we had a lesson on binary operations. I left you with an activity. So today we will start with an activity for you to actually follow up how to come out with a combination table. After that, we will now look at a series of activities on how to determine whether the operation forms a group, an abelian group, and the order of a group. So at this point in time, I'm going to read the activity, then you take it down. That is activity 1. The operation star is defined on the set S equals 0, 1, 2, 3 by x star y equals x plus y. S equals 0, 1, 2, 3 by x star y equals x plus y. First question. Draw an operation table for this information. That's A. Draw an operation table for this information. B. Determine whether S forms a group. B. Determine whether S forms a group. We already know the properties of a group. I told you in the last class that for an operation to form a group, it should be closed, it should be associative, it should have an identity element, and each element should have an inverse. So now we are going to draw the combination table or the operation table. I gave so many appellations for it. So I will start with the operation table. You have your operation here, star, and I have my vertical line. Here I have my horizontal line, and I will now fill in the numbers. 0, 1, 2, and 3. I'm filling both vertically and horizontally. So here you have 0, 1, 2, and 3. Okay, now row horizontal lines, column form and row form to separate the numbers. I'm done with that. Now it's time for me to actually demonstrate what we have with respect to that question. To come out with a table now, recall, we are taking an element from the vertical and we are adding to another element in the horizontal to give the final result, because we are told that x star y is equal to x plus y. Okay, so now I'm starting the activity. Please, you look up, you need to be very, very attentive here. All the elements here on this column vertically, they represent x, and the ones horizontally, the row, they represent y. So we start. If x is 0 and y is 0, I'll put it here. 0 plus 0 is 0. 0 and 1, that's 0 plus 1, 1. 0 and 2, 2. 0 and 3, 3. Okay? Now we go to x again. We are now on the second row. X is 1, y is 0. If I add, my result is 1. X is 1, y is 1. If I add, my result is 2. X is 1, y is 2. If I add, my result is 3. X is 1, y is 3. If I add, my result is 4. Okay, I'm done with that. We take the next one, 2 and 0. 2 plus 0 is 2. 2 plus 1 is 3. 2 plus 2 is 4. 2 plus 3 is 5. Next, 3. 3 plus 0 is 3. 3 plus 1 is 4. 3 plus 2 is 5. 3 plus 3 is 6. You see, I have come out with my table. Now, how do I determine whether this thing actually forms a group? That's my table. Everybody satisfied with that? So I draw a line here. I want to determine whether it forms a group now. Okay, the first property, closure. We said for a set to be closed, all the elements we have in the table must belong to the given set above. If you look at the set we have above, the set is S equals 0, 1, 2, 3. But if you look at the table, it's got that we have some strange elements. We have 6, we have 5, and we have 4. So this is not closed. So now conclude that S is not closed. I'm done with the first property. And now, if one of these things fails, it cannot form a group. If one of these properties fails, it cannot form a group. The set will never be a group. We should be very careful with this. Initially, you discover that it's not closed. So, closure did not hold. So automatically, my set S is not a group. It cannot form a group. Now, we are going to examine other properties you have in your notes. I gave you the notes already. The properties are identity. That's the next one. Identity, where we say if you take an element and you operate it with an identity element, the result must give the element itself. Okay? Now, since I have strange elements here, it will be very difficult for me to have identity at a certain point. Now look at it. If I take any element and operate the identity, I have the element itself. If I take 0 and 0, I have 0. 1 and 0, I have 1. This and 0, I have 2. 3 and 0, I have 3. You see, that is how you look at it from the table. So it's called if I take 0 and 0, I'll have 0. 1 and 0, I should have 1. 2 and 0, I should have 2, according to what I'm seeing on my table. Then 3, operated with 0, my result will give 3. So we are going to conclude this column automatically forms the identity element. So now conclude. Right by saying it implies identity element is noted with letter E is equal to 0. Next, I will take the next property, and that is inverse. We said for the inverse property, if you take an element and you operate it with the inverse, the result must give identity. This is what you do. If I take an element and operate with the inverse is denoted a to the power negative 1, the result must give e, which is the identity element. So I'm going to pick some elements here and try to verify their inverses. If I take an element according to my table and operate it with the inverse, I should have identity. And my identity element is 0. So I go to my table and look for where I have identity on my table. When I take 0 and 0, I have 0. That's the answer. Which means if I operate 0 with the inverse 0, I should have my identity 0. So now conclude that inverse of 0 equals 0. If you look at the second column, there is no 0. If I take 1 and operate with anything here, I will never have 0. If I take 2 and operate with any number here, I will never have 0. If I take 3 and operate with any number, I will never have 0. So in that case, other elements do not have their inverses. So you see, it's already proven to us that this thing will never form a group because not all the elements have inverses. Then we'll go to associative property. We said for associativity, we are dealing with 3 elements. If I take an element A and operate it with another B and the third element C, expressed in this form, our result should always be the same as when I take A and B in brackets and I operate with C. At this point, I can pick any 3 elements here. I can take 1, 2, 3 or 0, 1, 2. So let's consider A to be 1, B 2, C 3, and we substitute in the formula. So I have 1 star 2 star 3 like this. Please should be very careful here. It should be equal to 1 star 2 star 3. Let's verify now. 2 star 3, go to your table. 2 star 3, my answer is 5. So I'm left with 1. What we have in the bracket has given us a result 5. Should be equal to, now 1 star 2. You take 1 for x, you operate it with 2, the result is 3. So I left with 3 here, star 3. Recall in board maths we say always work with what is in the bracket, so that's why I started with the things in brackets according to board maths. The next, we'll now look for 1 star 5. Do we have 5 there? No. 3 star 3. 3 star 3 will give 6. Good. So this one has a question mark. So in that case, it is not associative. Hence, the operation is not a group. Now, we need to verify whether it forms an abelian group. That's what I said. I'm going to verify all the properties. Okay. Therefore, see. For abelian groups, it must be commutative. For a group to be abelian, it should be commutative. Commutative here in the sense that if you take any two elements and you carry out an operation, the result should be the same as when you reverse the position of the elements. What am I saying in essence? If I have an element A and I'm operating with another element B, it should give the same result as when I take B and operate with A. Right? So in this case, we are verifying the properties. So we have A, we can take any element A, could be 0, and you operate with 1. It should give the same result as 1 operated with 0. Okay, now 0 operated with 1, my answer is 1. 1 operated with 0, my result is 1. So you discover that they are the same. Since the result is the same, we now say hence it is an abelian group. It is an abelian group. It is an abelian group since it is commutative. Yes. For a group to be abelian, it must be commutative. I already gave the definition for commutativity in our last class. Alright. Now we need to verify the order. That's the next thing we're talking about under group theory. We talk about the order of a group. Order of a group. The order of a group here refers to what? The number of elements in that group. So the order is the number of elements in the group. And if you look at the set we have, S is 0, 1, 2, 3, 4. Though S does not form a group. If S had formed a group, then the order will be 4. We just have 4 elements. You count the number of elements in that set. The number of elements in that set gives a group. Okay, but this exercise here was for us to know how to come up with the operation table and also demonstrate the different properties of a group. We have seen it. So I'm going to give another challenging exercise or activity for you to go through, and then we look at the solutions together. So while you take down the solution to that exercise, I will need to also give you more exercises and some definitions that are very important for you to have a mastery. Okay, so I believe that since a video, you are going to follow the instructions as required. So after copying from the first step of the exercise right up to the case where you conclude that it is not associative and hence does not form a group, you stop there. Then you now write abelian group. So we want to define abelian group. So we say a group is abelian if it is commutative. I have already demonstrated that property of commutativity. That is it. Then the next definition will be order of a group. This is the number of elements of a group. This is the number of elements of a group. E.g., I've demonstrated that e.g., if S, that's order of a group. If S equals 1, 2, 3, define your writing, please. Order of a group. This is the number of elements of a group. E.g., if S equals 1, 2, 3, define on the operation star is a group, then the order is 3. Then the order is 3. If you look at it, we have 3 elements. Since S has formed a group, we're talking about the order of a group. So it must form a group for us to state the order. So then the order is 3. Alright, now we'll take another activity. We're going to take this activity. Activity is consider, that's activity 2. Consider the operation star defined on the set S. Consider the operation star defined on the set S equals 0, 1, and 2 by multiplication modulo 3. Multiplication modulo 3. Multiplication modulo 3. A. Construct an operation table for the above operation. A. Construct an operation table for the above operation. The above operation here is star. B. Determine whether star forms a group. Determine whether star forms a group. C. Verify if S is an abelian group and determine the order of the group if it exists. C. Verify if S is an abelian group and determine the order of the group if it exists. Okay, all right. So that is the activity you will do for me, and we will come back to that. I take it over again. Consider the operation star defined on the set S equals 0, 1, 2, 3 by multiplication modulo 3. I already explained modulo 3. Modulo means you multiply or you are adding and then you divide and write down the remainder. If you are multiplying like this case, it means you multiply the numbers by 3 and then you multiply the numbers, you divide and write down the remainder. You are dividing by 3. Multiplication modulo 3 means you multiply the numbers, divide by 3 and write down the remainder. I take it over again. Multiplication modulo 3 means multiply the numbers, divide by 3 and write down the remainder. If I'm talking about multiplication modulo 4, you multiply the numbers, divide by 4 and write down the remainder. You are writing down the remainder. Alright, I think that is that for our lesson. So maybe I will take the last activity again for you to actually follow up since you are copying. I say consider the operation star defined on the set S equals 0, 1, 2, 3 by multiplication modulo 3. A. Construct an operation table for the above operation. B. Determine whether the set S is a group. C. Verify if S forms an abelian group and determine the order. Alright, thank you. Wish you all the best and have a nice day. See you in our next lessons. So in our next class, I expect you to have solved this and pose your worries or your difficulties so that I can revise them again with you for you to actually have a mastery of the lesson. Thank you.